Welcome to AudioCert, where the official study guides are brought to life. Today we're embarking on what I think is a really crucial exploration into cloud computing. Specifically, we're delving into Module 19 of the EC Council Certified Ethical Hacker, or CEHv13 official study guide. Our goal here, as always, is to sort of unpack these, well, often complex concepts, distill the essential knowledge, and give you a clear path to being, incredibly well-informed about cloud security, especially from an ethical hacker's viewpoint. It's a huge landscape, really dynamic, but we'll navigate it together, make it actionable, make it clear.
Indeed. And, for anyone in cybersecurity today, really getting cloud computing isn't just like a nice to have. It's absolutely essential. The cloud, it's gone way beyond just storing photos, right? It's the fundamental engine powering pretty much every modern business you can think of, from tiny startups to massive global players. So what that means is it's not just driving innovation, it's also, crucially, a prime target. A target for ethical hackers looking to shore up defenses, and unfortunately, for malicious actors hunting for weaknesses. So we'll start by laying out the foundation services, deployment models, then we'll move into some of the more advanced tech, and really importantly, the attack techniques, and of course, the solid defense strategies.
Wow.
We'll start right at the basics, what the cloud is, how it functions, before peeling back those layers on its vulnerabilities.
Okay, that sounds like a really solid plan. So let's start right there at the beginning. When we talk about cloud computing, what are we really talking about?
Fundamentally.
Well, at its heart, it's about computing services being delivered over the internet. Simple as that, really. All right, sounds simple, but I know from the material, it often hides a lot of complexity. That can make troubleshooting and definitely securing it pretty challenging. I like the analogy of home utilities. You flip a switch, you get power, you don't own the power plant, you don't manage the grid, you consume the service when you need it. Cloud computing kind of offers that same deal for computing resources, doesn't it?
Yeah.
Like processing power, storage, software.
Exactly. You access it, you use it, but you don't have the headache of owning or managing all that complex underlying infrastructure.
Okay.
And that shift, that move to shared resources, on-demand availability, that completely changes how we have to think about security. Take something specific, like a firewall as a service, or FWAS. This isn't your old physical box blinking in a rack. It's a cloud service. It filters network traffic intelligently, protects against threats, both internal and external. Often uses things like Internet Protocol Security IPsec for secure links.
Right.
And FWAS gives you advanced stuff like better data analysis, malware detection, deep packet filtering, network analysis. You see this with providers like Zscaler Cloud Firewall or Security HQ. The key thing for an ethical hacker, though, is your focus shifts, right? You're not just looking at one static box. You need to understand distributed policies, API-driven configurations, often across a massive network. Get one policy wrong there, and boom. It can become a single point of failure affecting huge parts of an organization's setup.
That's a really critical point, how the security perimeter just dissolves almost. So to really get a grip on who's responsible for what in this new world, we need to understand the different flavors of cloud services. There are the three main types, right? Infrastructure as a service, IaaS, platform as a service, PaaS, and software as a service, SaaS. Let's maybe use that house analogy. I think that really helps make it clear.
Yeah, that's a good one.
Okay, so if you do things the old way, on premises, it's like you buy the land, you design the house, build it from the ground up, furnish it, and then you're responsible for absolutely everything. Applications, data, runtime, OS, virtualization, servers, storage, networking hardware, the whole lot, all yours.
Right. Total control, total responsibility.
Then with the IaaS, you're essentially renting the land and the foundation from the cloud provider. They give you the core infrastructure, server, storage, networking, the virtualization layer.
Yep.
But you still build the house, furnish it, maintain it. So you manage the OS, runtime, your apps, your data.
You handle everything above the hypervisor, basically.
Exactly. Moving on to Pesio, now it's more like renting a house that's, well, mostly built for you. The provider handles the core structure, the utilities runtime, OS, virtualization, servers, storage, networking. Your main job is to furnish it with your apps and data and then live in it. You don't worry about the plumbing or the foundations.
Right. They manage the platform. You manage what runs on the platform.
Perfect. And finally, SaaS. This is like renting a fully furnished apartment. Everything's managed for you. You just show up, use the software. Your main responsibility is usually just your data within that app and managing who gets access. Everything else, apps, runtime, OS, infrastructure, all handled by the provider.
That house analogy does a great job illustrating this really, really critical concept, the separation of cloud responsibilities. For an ethical hacker, Knowing these models inside out tells you exactly where to focus your testing. If a client uses IaaS, you're going to be looking hard at their OS hardening, their network security groups, their application security. But if they're mainly SaaS, your focus shifts completely. You're looking at data access controls, user identities, how the SaaS app itself handles sensitive info. And honestly, misunderstanding these lines, that's where I see so many vulnerabilities crop up. People assume the provider handles all the security, but often a huge chunk still sits with the customer.
Yeah, you've really hit the nail on the head there. That shared responsibility model is just so fundamental. It makes me wonder, though, where do organizations most commonly kind of mess up or misinterpret their responsibilities, even when they know the model?
That's a great question, because even with the model clear, the biggest trip up is almost always configuration. Like in IaaS, yeah, the provider secures the hypervisor, but the customer controls the network config within their virtual private cloud. So they might leave security group ports wide open to the internet by accident,
Right,
or maybe too permissive.
right. Easy mistake to make.
Or with Proprius, the provider manages the runtime, sure, but the customer is still responsible for securing their application code running on it. And that code might pull in vulnerable libraries or have poor input validation, things like that. It's almost always that layer of configuration and application logic, the stuff the customer manages, where the gaps appear most often.
That makes total sense. It's the stuff you control that you have to secure. Okay, so let's shift gears a bit and talk about where these cloud services actually live. The choice of deployment model, it depends on what the company needs, right? Like location, security, sharing, management, customization.
Exactly. Different needs, different models.
First up, the one everyone knows, the public cloud. Services like apps, server storage, all available to the public over the internet. Provider creates it, maintains it, usually pay-per-use. Think Amazon EC2, Google App Engine, Azure Services Platform.
The utility model again.
Then private cloud. This is infrastructure just for one single organization. Often inside their own security perimeter, users access it from within that perimeter. Gives you more control, helps with compliance stuff.
Right. More control, potentially higher cost.
Then there's community cloud. This is interesting. It's multi-tenant, shared infrastructure, but shared among organizations with common needs. Maybe they all have the same security or compliance requirements. Can be on-prem or off-prem. Advantages: cheaper than private, flexible, scalable shared resources. But downsides too, maybe competition for resources. Hard to predict usage. Some security worries about data access between tenants, trust issues, legal liability.
Yeah, community clouds are a bit of a balancing act. You get some benefits of scale, but you inherit some risks from sharing.
And finally, hybrid cloud. This is a mix, right? Two or more clouds, private, public, community, but they're linked together somehow. Classic example. Keep your really sensitive customer data on a private cloud, but run your website front end or maybe bursty workloads on a public cloud for cost or scale.
And the why for hybrid is usually pretty compelling. It offers that flexibility, it helps optimize cost to run things where it's cheapest or performs best, and it can definitely help with data sovereignty, keeping certain data within specific geographic or security boundaries. But, and this is a big but for ethical hackers, how do you manage security across these connected but different environments? It's not just securing two separate things. You have to secure the links, the data flows between them, and that creates a whole new attack surface right at those connection points.
Yeah, that connecting tissue, the glue holding it together, that sounds like exactly where things could get missed. And just when you think you've got the main models down, the cloud world throws more at you. Beyond those standard four, now we're hearing about multi-cloud, distributed cloud, and polycloud.
Landscape keeps evolving.
So multi-cloud, this is using services from multiple different cloud vendors at the same time, right? Like maybe using AWS for compute, Azure for databases, and GCP for AML stuff. The main idea is spreading your assets out. Increase resilience, get more power or storage options, reduce the risk if one provider has an outage. Tools like Azure Arc or Google Anthos help manage this kind of complex setup.
Right. Vendor diversity for resilience and best-of-breed services.
Then, distributed cloud. This sounds different. It's like one central cloud management plane, but it controls cloud infrastructure that's geographically spread out. Public or private clouds, but distributed. Users access data like it's local. This really enables edge computing, doesn't it? Great for things like AI, ML, IoT, where you need processing closer to the user or device. Advantages seem clear. Better performance, less latency, consistent management. But the downsides? Maybe new security vulnerabilities in those distributed locations, higher network costs, complex troubleshooting.
Exactly. Distributed cloud pushes infrastructure out, which is great for performance, but managing and securing that distributed footprint becomes the challenge.
Okay, and finally, polycloud. This isn't just using multiple vendors like multi-cloud. It's about picking and choosing specific features or types of cloud services from different clouds, potentially different vendors, and integrating them onto a single platform for a very specific need. It's more granular than multi-cloud.
Yeah, that distinction is subtle but important. Think of multi-cloud like going to different specialist restaurants for different courses, Italian for pasta, Japanese for sushi. You appreciate each vendor's strength. Polycloud is more like being a master chef. You go to the Italian place just for their specific, perfect truffle oil, and the Japanese place only for their absolute best, sashimi-grade tuna. Then you combine those specific ingredients back in your own kitchen to create a unique, highly specialized dish. It's about integrating best-of-breed features, not just vendors. And for an ethical hacker, this complex integration, the custom APIs, the gateways stitching these specialized services together, that's often where subtle vulnerabilities hide.
That chef analogy really nails it. Makes a complex idea pretty clear. Okay, before we jump into the really new tech, let's quickly touch on a couple of things that provide some structure here. NIST, the National Institute of Standards and Technology, they have a cloud computing reference architecture. It's like a framework, right? Helps understand the main players, activities, functions in the cloud, gives a common language.
Provides a standardized way to think about the components.
And within that, there's the concept of a cloud broker. What's that about?
Ah, right. As cloud services get more complex, sometimes organizations don't want to manage it all directly. A cloud broker acts as an intermediary. They manage cloud services for the consumer, maybe handling billing, optimizing costs, adding security layers, managing identities across different clouds. They basically sit between the provider and the consumer, adding value.
Gotcha. Makes sense. And all these services, they generate and need tons of data, which leads us to cloud storage.
Yep. And the architecture behind cloud storage is pretty sophisticated. It's built on distributed resources, designed for high fault tolerance using redundancy. Data gets replicated across multiple locations to ensure consistency, and the whole system aims for high durability, meaning your data should survive hardware failures. Think of services like Amazon S3 Simple Storage Service or Oracle Cloud Storage, Azure Storage, OpenStack Swift. They spread your data out, so if one disk or even one whole data center has an issue, your data is still safe and accessible somewhere else.
Okay, that covers the foundations really well. But with all this complexity, all this distribution, how do demanding new technologies even fit in without, breaking the bank or overwhelming the network?
That's a perfect segue, actually, because these new technologies are absolutely pushing the cloud to its limits and also benefiting hugely from it.
Emerging cloud technologies and core distinctions.
Let's talk about virtual reality and augmented reality on the cloud. VR and AR, they need massive computing power, right? Especially for graphics.
Oh, huge amounts.
So putting them on the cloud makes sense. What are the key benefits there?
Well, the big one is access to serious hardware without buying it yourself. The cloud gives you on-demand access to powerful multi-core CPUs and, crucially, high-end GPUs. This speeds up the rendering, the digital engines for VR, without needing a super expensive gaming PC locally for every user.
Right, so it lowers the barrier to entry.
Exactly. And it helps with software delivery, too. Developers can update the VR software seamlessly in the cloud. Users don't need constant local installs. Plus, the pay-per-use model works well. You might only use a high-end VR app occasionally, so you only pay for that heavy compute when you actually need it. Makes it way more cost-effective.
So the cloud is basically democratizing access to this cutting-edge tech, making it more efficient, more accessible.
That's a perfect way to put it. It removes that huge upfront hardware cost, fosters innovation.
Very cool. Okay, now let's clear up some terms that get thrown around a lot, sometimes incorrectly. Cloud versus fog versus edge computing. These are related but distinct, right?
Critically distinct, yes. Understanding the difference is essential.
So we know cloud computing is our baseline. Centralized, massive data centers, often far from the user, doing real-time processing.
The big brain in the distance.
Then fog computing. This is like a layer between the cloud and the devices out at the edge, right? It's distributed closer to where the data is generated, like from IoT devices. Millions of fog nodes. Think smart cities, smart grids, connected cars. It does some analytics and processing locally.
Exactly. It extends the cloud's intelligence closer to the action, handles stuff where low latency matters or where the connection back to the main cloud might be spotty. Advantages are lower latency, more agility, avoids sending everything back to the cloud. The main drawback is it's not quite as massively scalable as the central cloud.
Okay, and then edge computing. This is even closer to the source, like a subset of fog.
Right. Edge computing pushes the processing right down to the devices themselves, or very, very close to them. Billions of edge devices.
Think of processing happening directly on a sensor or a small gateway right next to a machine on a factory floor. It's for really small, urgent operations needing millisecond response times. Fog is more at the local network level. Edge is right at the data source. So why did fog and edge even come about? Is it just the sheer amount of data from IoT?
That's the primary driver, absolutely. The Internet of Things explosion. Billions of devices, self-driving cars, factory sensors, smart meters churning out data constantly. Sending all that raw data back to a distant cloud creates huge problems. Massive latency delays, eats up incredible amounts of bandwidth, raises data privacy concerns. Fog and Edge solve this by processing data locally, reduces delays, saves bandwidth, enables real-time decisions right where they're needed.
Makes sense. So how do they compare on security?
That's a key differentiator. Cloud. Centralized. Those thousands of data centers.
Yeah.
Real-time processing. Generally considered the most secure environment because data centers are physically secure, huge budgets for security teams, etc. Fog. Distributed, millions of nodes, does caching, optimization. Also designed to be highly secure, often in controlled network locations, but maybe not quite as fortified as a major cloud data center. Scalability is more constrained than the cloud. Edge. Decentralized. Billions of devices. Real-time processing right near the device. And this is the important part. Generally considered less secure than fog.
Less secure. Why is that?
Think about where edge devices live. They're often out in the physical world, sensors on pipelines, cameras on lampposts, controllers on factory floors. They can be physically accessed or tampered with more easily. Plus, they usually have limited computing power and memory. They can't run complex security software or heavy encryption easily. Patching and monitoring billions of distributed edge devices is also a nightmare compared to managing servers in a data center or even fog nodes in a local network. That makes them a softer target.
Okay, that physical vulnerability and management challenge makes sense. Can we use that concert analogy again to tie cloud, fog, and edge together?
Yeah, let's do it. Imagine that huge global concert again. The cloud is the main recording studio. Far away, massive resources, where the final album gets produced, mixed, mastered, archived for the long term. Centralized, powerful, secure. Fog computing is like the live mixing desk set up at each concert venue. It's distributed, closer to the live performance. It does real-time sound adjustments, optimizations for the audience right there, extends the studio's capability locally. And edge computing, that's the individual musician's effects pedal right on stage, processing the guitar sound immediately right at the source for those instant millisecond effects. Closest to the action handles urgent small tasks. Each layer, cloud, fog, edge, plays a distinct role, operates at a different proximity to the data source, and comes with its own security considerations.
That really clarifies it. Cloud is the studio, fog is the venue mixing desk, edge is the effects pedal.
Got it. Okay, let's move on to something absolutely fundamental to how modern cloud apps are built and run. Containers and orchestration.
Containers and orchestration, the power of packaging.
So first, the basics. What exactly is a container?
Okay, think of it as a standardized box. It's a lightweight, standalone package containing a piece of software, your application, and everything it needs to run. All its dependencies, libraries, configuration files, binaries, system tools, runtime, everything. The really crucial part is that it runs reliably and consistently, isolated from other containers and the underlying system.
Right, like that shipping container analogy. It doesn't matter what's inside closed electronics. As long as it's in the standard box, it can go on any ship, any train, anywhere in the world, and it arrives ready to function. The container holds everything the app needs to work anywhere. And cloud providers offer this as containers as a service, or KaaS, right? Exactly. And that shipping analogy highlights the biggest win, solving compatibility issues. You know, the classic developer line, well, it worked on my machine. Containers pretty much eliminate that.
Yeah.
Because everything the app needs is bundled inside the container. It runs exactly the same whether it's on a developer's laptop, a test server, or in production in the cloud. That consistency is huge.
Okay, so consistency is key. What are the other big advantages?
There are several major ones.
Let's walk through them. First, security. How does the isolation help?
Well, because each container is sandboxed, if one application inside a container gets compromised, the infection is much less likely to spread. It's contained, literally.
Yeah.
Harder to break out and affect the host or other containers.
Okay, that makes sense. What about efficiency and cost?
They're incredibly efficient. Compared to virtual machines or VMs, they use way fewer resources. They don't need a whole separate operating system for each one. They share the host OS kernel. So they often only need megabytes of memory. not gigabytes like VMs. You can run many more containers on the same server, which saves money. And that isolation also means if one app crashes, it doesn't usually take down others on the same host.
More bang for your buck, basically. And scalability.
Built for it. It's super easy to add more identical containers to handle increased load. You just spin up more copies. And there's smart scaling too. You can automatically scale up when needed and scale down, even put unwanted containers at rest to save resources. Very dynamic.
And lastly, robustness. Sounds like speed is a factor here.
Absolutely. Containers can be created, started, stopped, and destroyed in seconds. VMs take minutes to boot up because they have a full OS. This speed makes development much faster. You can deploy updates, fix bugs, roll out new features incredibly quickly. Much more agile.
So that resource efficiency is really because they share the host OS kernel, unlike VMs which need a full OS each.
Precisely. VMs carry the weight of a full OS, kernel, libraries, everything. Containers just package the application and its direct dependencies, then share the underlying host OS. That's the fundamental difference that makes them so lightweight and fast.
Okay, that leads perfectly into the comparison. Containers versus virtual machines, VMs. We know virtualization is the bedrock of cloud computing, letting multiple OSs run on one physical machine. VMware, Hyper-V, those guys.
The original enabler.
VMs were great for portability and isolation compared to bare metal, but they have drawbacks, right? Heavy, needing that full OS, slower performance, can be tricky to move between different virtualization platforms, takes time to provision.
Yep, those are the main pain points.
And containers were designed specifically to fix those issues. Lightweight, megabytes, share the host kernel, boot in seconds. Let's use that house analogy again. VMs are like having multiple separate houses on one plot of land. Each house needs its own foundation. Walls, roof, utilities, electricity, plumbing. Independent, isolated, but resource heavy. Containers are like having multiple apartments within one large building. Each apartment has its own living space and furniture, your app, its data. But they all share the building's core foundation and utilities, the host OS kernel, infrastructure. Much lighter, faster to set up, more efficient use of the underlying land.
Perfect analogy. It captures that shared infrastructure benefit beautifully. Containers address the VM overhead, making software truly run anywhere without the usual headaches. It's why they're central to modern cloud-native development.
And when you talk containers, you have to talk about Docker. It's basically the standard, isn't it? The container king.
Pretty much, yeah. Docker really popularized containers and made them accessible. It's open source technology for, well, developing, packaging, and running apps in containers. It provides that platform as a service experience using OS-level virtualization. It delivers those self-contained packages we've been talking about.
And the big sell is package your app and its dependencies into a Docker container, and it runs the same everywhere. Laptop test, production, any cloud.
That's the promise, and it largely delivers. Isolation ensures apps don't interfere with each other. They communicate through defined channels.
How does Docker actually work, architecture-wise?
It's a client-server model. You interact with the Docker client, the command line tool usually. The client talks to the Docker daemon, that's the background service, the brains, which actually builds, runs, and distributes the containers. They communicate using a REST API, usually over a Unix socket or a network interface.
Okay. And there are some key Docker objects we should know.
Yeah, a few core concepts. Images. These are the blueprints. Read-only templates with all the instructions needed to create a container, like a recipe. Containers. These are the running instances created from an image. The actual shipping container doing the work. Services. These let you scale containers across multiple Docker daemons. You define how you want your app to run, stamping through replicas, and Docker Swarm. Its native clustering makes it happen. Networking. Docker manages the networks that allow isolated containers to communicate with each other or the outside world. Volumes. This is crucial for data that needs to persist. Volumes are dedicated storage areas managed by Docker, separate from the container's lifecycle, so your data doesn't disappear when the container stops.
Got it. And Docker fits really well with the microservices architecture, right? Instead of one giant application, you break it into smaller, independent services.
Exactly. Microservices is an architectural style. You break down big, monolithic apps into smaller, focused services. Each service does one thing well and communicates with others over the network, often using APIs. And very commonly, each microservice runs in its own Docker container. This allows teams to develop, deploy, and scale each service independently. Gives you a ton of flexibility and resilience.
Okay, so Docker lets us package individual services neatly. But if you have lots of these containers, potentially hundreds or thousands for a complex application, Managing them all must be a nightmare.
You've hit on the next crucial piece of the puzzle. That's precisely where Kubernetes comes in, often shortened to K8's K, 8 letters, S.
K8s, the orchestrator.
Exactly. Developed by Google, now open source. Kubernetes is an orchestration platform. It's designed specifically to manage containerized applications and microservices at scale. It provides that resilient framework. It handles deploying containers, scaling them up or down, managing failover if something breaks, ensuring redundancy, all automatically. It takes the management headache away. In a real production environment where you need zero downtime, Kubernetes is pretty much essential for managing complex containerized apps. If one container fails, K8 notices and starts another one, often seamlessly.
So if Docker containers are the individual musicians, Kubernetes is the conductor, the stage manager, the sound engineer, making sure the whole orchestra runs smoothly, even if one player messes up.
That's a great way to think about it. It handles all the coordination, and it has a ton of powerful features. Service discovery helps containers find each other automatically. Load balancing spreads traffic evenly across multiple instances of a container. Storage orchestration lets you attach different kinds of storage, local, cloud, to your containers easily. Automated rollouts and rollbacks manages updates smoothly and lets you easily undo them if something goes wrong. Automatic bin packing figures out the best place to run containers based on their resource needs. Optimizing server usage. Self-healing automatically restarts failed containers, replaces them, kills ones that don't respond, keeps things running. Secret and configuration management securely handles sensitive stuff like passwords and API keys, keeping them separate from the container images.
Wow, that's a lot of automation. How is it structured?
Basically, a Kubernetes cluster has two main parts: the master node, or control plane, and the Kubernetes nodes, worker nodes. The master node is the brain. It has components like the kube app server, the front door for all commands, and a key target for attackers trying to bypass auth or cause denial of service. The kube scheduler decides where new pods run can be manipulated to exhaust resources, and crucially, etc., is a highly reliable key value store that holds the entire state of the cluster. Configurations, secrets, everything. Compromising, etc. is like getting the keys to the kingdom. It's a massive target. The nodes are where your actual containers run. Each node runs kubelet, an agent that talks to the master and makes sure containers are running, and kubeproxy manages network rules. All these pieces work together. Running your app across multiple nodes gives you that high availability and scalability, but yeah, it also increases the potential attack surface if things aren't locked down properly.
Okay, so Kubernetes is incredibly powerful for operations, but power often comes with complexity and risk, right? Despite all the benefits, containers and Kubernetes must introduce some new security challenges.
Oh, absolutely. They solve some problems, but create new ones for security teams and ethical hackers.
Like what? What are the big ones?
Well, first, there's the inflow of vulnerable source code. Containers heavily rely on base images, often pulled from public repositories like Docker Hub. These images can contain outdated libraries, known vulnerabilities, sometimes even deliberately malicious code. If you don't scan your images meticulously, you're inheriting risk.
Okay, so trust but verify for images. What else?
Compromising sensitive information secrets. Containers often need passwords, API keys, tokens to talk to other services. If these secrets are handled badly, like hard-coded into the image, passed as environment variables insecurely, stored in world-readable config files, attackers who get access to the container or its configuration can steal them, that's a huge issue.
Right. Secrets management is critical.
Then there's the speed of DevOps. Containers are designed to be ephemeral, start fast, do a job, stop, disappear. This fugitiveness is great for agility, but it can also help attackers. They can launch quick attacks from a container and then vanish, leaving very little trace for forensics. Makes detection harder.
Hiding in the churn. What about the isolation? Can it break down?
Yes, isolation breakdowns are a concern. While containers are isolated, vulnerabilities have been found in container runtimes, like Docker itself, or, more commonly, in the underlying Linux kernel that all containers on a host share. A severe vulnerability could allow an attacker to escape the container and gain access to the host system or other containers. That's a major escalation.
Container escapes, okay.
And finally, insecure communication. Containers need to talk to each other, to the host, to external services. If this communication isn't properly encrypted, if authentication between services is weak, or if network policies aren't strict enough, attackers can potentially intercept traffic, spoof services, or move laterally within the cluster.
So putting it all together, this dynamic, distributed, fast-moving container world makes traditional security harder. Things designed for static servers struggle.
Exactly. Traditional security tools often lack visibility into container lifecycles and inter-container traffic. It requires new tools, new approaches focused on the container runtime, the orchestrator, like Kubernetes, and the application code itself. It's a big shift. For an ethical hacker, it's a fascinating new landscape to explore. For defenders, it's a constant challenge to keep up.
That really highlights the security paradigm shift. Okay, so let's look at the next evolution. Serverless computing. If you're not managing servers at all in serverless, does that make it inherently more secure, or does the risk just move somewhere else?
That's the million-dollar question, isn't it? And yeah, it's a common misconception that serverless equals no security worries. It definitely removes the burden of patching servers, managing OS security, but the risk doesn't disappear. It absolutely shifts, often to areas that are trickier or less familiar.
Serverless computing focus on code, not infrastructure.
Okay, so let's define serverless computing. It's another emerging tech built on containers and microservices. But the key ideas are pay-per-use and no server management for the developer, right?
Exactly. The developer just writes code of function and uploads it to the cloud provider. The provider handles everything else, provisioning the infrastructure, scaling it up or down based on demand, patching the OS, all of it.
The analogy here is ordering food from a restaurant. You care about the meal, your code function, but you have no idea and don't need to care how the kitchen, the servers, is run.
Perfect analogy. Developers focus purely on the application logic. They don't need deep expertise in cloud infrastructure. The provider takes care of making sure the code runs when it's triggered by an event, maybe an API call, a file upload, a database change, and critically, the function usually runs, does its job, and then the underlying container is automatically destroyed. You only pay for the milliseconds or seconds it was actually executing. Think AWS Lambda, Azure functions, Google Cloud functions. It's incredibly agile and can be very cost-effective.
Super agile. But how does it compare directly to using containers in a more traditional way, like with Kubernetes? What are the key differences?
Good question. They overlap but have distinct characteristics. Containers, they generally run continuously until you stop them. They need server resources even when idle. No inherent time limit on execution. Data can be stored in attached volumes. Good for complex apps, microservices, long-running processes. You choose your language, your runtime. Serverless. Functions are ephemeral, auto-destroyed after execution. You only pay for execution time. There's usually a timeout limit, for example, 15 minutes for Lambda. Data persistence typically relies on external services like object storage, S3, blob storage, or databases, mainly suited for event-driven microservices or short tasks. Language choices are restricted by what the provider supports.
Okay, so those differences, ephemeral nature, provider management, reliance on external services, must really change the security game, right? How does it impact the attack vectors for an ethical hacker?
It changes the focus significantly. You're not attacking a persistent server anymore. You're often attacking the function's inputs, its permissions, or the event triggers that invoke it.
So does this mean classic web vulnerabilities like SQL injection or cross-site scripting just vanish? Or do they find new life in serverless?
Oh, they definitely find new life, sometimes in trickier ways. Serverless apps are still vulnerable to many of the same serverless security risks as traditional web apps. XSS, SQL injection, DOS, broken off. They're all still relevant.
OWASP has a top 10 specifically for serverless, doesn't it? What are some key risks there and why are they challenging in this context?
Right. Let's hit a few highlights. A1 injection, still a huge problem. Untrusted data comes in maybe via an API gateway event and gets processed by the function. If not validated properly, it could lead to command injection within the function's temporary environment, maybe leaking environment variables with secrets, or SQL injection if the function talks to a database. The ephemeral nature makes tracing the attack harder. A2 broken authentication. If the mechanism triggering the function, like an API gateway endpoint, isn't properly secured, attackers could potentially invoke functions they shouldn't, executing code or accessing data. A3 sensitive data exposure, still critical. Maybe the function logs sensitive data to CloudWatch or writes it unencrypted to an S3 bucket it has access to, or returns too much sensitive info in its response. A5 broken access control. This is a big one in serverless. Functions run with IAM roles. If that role is overly permissive, giving the function access to resources it doesn't actually need, then compromising that function gives the attacker excessive privileges to move laterally or access data across your cloud account. Least privilege is vital. A9 using components with known vulnerabilities. Functions rely on libraries and dependencies just like any other code. If you pull in a vulnerable third-party package, your serverless function inherits that vulnerability. Supply chain security is just as important here.
So the stateless and event-driven nature makes traditional monitoring harder. And attackers' actions might be incredibly brief.
Exactly. Milliseconds of execution, then gone. Traditional network monitoring or host-based agents often miss it. Security needs to shift towards robust input validation at the function level, strict least privilege IAM rules, runtime protection that monitors function behavior, and really meticulous logging and alerting focused on function execution and API calls.
Okay, that sets the stage perfectly. We understand the tech, the risks. Now let's flip the script and talk about ethical hacking in cloud environments. From the ethical hacker side, how do we approach testing these complex systems?
Well, the classic phase is still applied, just adapted for the cloud. Reconnaissance, exploitation, and post-exploitation. And it's super important to stress, we're talking about authorized penetration tests here, working within agreed scopes and policies, often internally or with explicit permission.
Ethical hacking in cloud environments, exploiting the digital frontier.
Right, let's start with reconnaissance, gathering intel. What's involved in mapping out a target's cloud presence?
First step is identifying the target cloud environment. Are they on AWS, Azure.GCP? A mix. Tools like Shodan and Senses are gold mines here. They scan the internet and index services. You can use specific filters. Like in Shodan, search port.443 for HTTPS, ssl.issuer.issuer.issuer.amazon to find AWS stuff, cloud.region, region code to target specific areas, org.microsoft for Azure, product.kubernetes. This helps you understand their footprint and tailor your attacks to cloud-specific services.
Okay, so find out where they live. Then vulnerability scanning, tools like Prowler.
Yeah, Prowler is great. It's a multi-cloud auditing tool. Checks for hundreds of security best practice violations, misconfigurations, potential vulnerabilities, things like insecure data transmission, overly permissive IAM policies. It covers a lot. And it maps findings to compliance standards like CIS benchmarks, NIST, PCI DSS, API, GDPR. Really useful for finding common weaknesses.
And identifying misconfigurations with tools like CloudSploit. Misconfigs seem like a recurring theme.
They are the recurring theme in cloud security breaches. Cloud environments are just so complex, it's easy to miss a setting. CloudSploit specifically looks for these misconfigurations across AWS, Azure, GCP, public buckets, permissive security groups, unencrypted databases. It flags common security risks based on known benchmarks.
So Recon is all about building that detailed map of their cloud setup, finding the low-hanging fruit like misconfigurations.
Absolutely. Thorough recon is everything. It tells you where to focus your efforts. You're not just blindly attacking. You're strategically targeting weaknesses you've identified in their specific cloud deployment. You know, host, it reminds me of a pen test we did where simple recon using Google Dorks found a publicly exposed development server's Jenkins instance, default credentials still enabled. Game over right there, pretty much. All from basic recon.
Wow. A simple oversight leads to complete compromise. Okay, let's get into some specifics then, some real-world cloud platform hacking examples. Where does it get interesting for an ethical hacker?
Okay, let's look at some common techniques.
Starting with AWS hacking highlights. Enumerating S3 buckets. S3 storage is everywhere. Attackers are always looking for open buckets, right? How do they find them?
Several ways. Inspecting website source code for S3 URLs, brute forcing common bucket names or URLs using tools like Burp Suite, using those Google Dorks like integral.s3.amazonoz.com, confidential or similar terms, and specialized tools like S3 Scanner, Bucket Loop, Cloud Brute automate this. They try permutations, check permissions, sometimes even list contents if public. The nightmare scenario is finding a bucket accidentally set to public read that contains not just website images, but maybe database backups, configuration files with hard-coded keys, sensitive documents. Happens more often than you'd think.
Okay, finding open buckets is huge. What about compromising AWS IAM credentials? How do attackers get those vital keys?
Lots of ways, unfortunately. A big one is developers accidentally committing access keys to public Git repositories. Code scanning tools look for these. Classic social engineering phishing emails, tricking users into giving up credentials or running malicious code. Sometimes credentials used by the AWS command line interface, AWS, are stored insecurely on a compromised workstation, exploiting vulnerabilities in third-party software that has been granted AWS access. And of course, insider threats.
So protecting those credentials is paramount. What about the Instance Metadata Service IMDS attack?
IMDS. It's a service running on EC2 instances that provides info about the instance itself, and crucially, temporary credentials for the IMM role attached to the instance. Older versions, IMDS v1, were vulnerable to server-side request forgery, SSRF attacks. If an attacker could exploit an SSRF flaw in a web application running on the EC2 instance, they could trick the application into making requests to the IMDS endpoint, usually 169.254.169.254, and steal those temporary credentials. That could give them the privileges of the instance's role. The fix is enforcing IMDS v2, which requires a session token, making SSRF exploitation much harder.
Right, use IMDS v2. And if an attacker does get some credentials, maybe low privilege ones, how do they perform AWS IAM privilege escalation?
Several common paths. If they compromise a user or role that has permissions like IAM, create policy version, they can modify an existing IAM policy to grant themselves more privileges, maybe even administrator access. Or permissions like IAM, put user policy, IAM.group group policy, IAM.put role policy, let them attach new inline policies. The permission IAM.add the user to group lets them add their compromised user to a highly privileged group, like the administrators group. It's all about finding users or roles with specific IAM modification permissions and leveraging them.
Okay, lots of ways to move up in AWS. What about Microsoft Azure hacking highlights? How does Recon work there? Aid internals?
Yeah, Aid internals is a really useful PowerShell module for digging into Azure Active Directory and Office 365. Even from the outside, you can use commands like invoke a dint reconnaissance outsider to gather info about verified domains, tenant IDs, authentication endpoints. Helps build that initial picture.
And finding exposed storage, like publicly exposed blob storage with Goblob.
Similar idea to S3 buckets. Azure uses blob storage. Goblob is a tool that tries to enumerate common storage account names and container names within those accounts. If a container is accidentally set to public access, Goblob can find it and list the files, potentially revealing sensitive data.
What about exploiting Azure services themselves, like managed identities and Azure functions?
That's a more advanced technique. Managed identities let Azure resources, like a function app, authenticate to other Azure services securely without needing stored credentials. If an attacker finds a vulnerability, say command injection, in an Azure function, they might be able to execute code that retrieves the managed identity's access token. Once they have that token, they can use it, acting as the function app, to access whatever other Azure resources the managed identity has permissions for, maybe list storage accounts, read secrets from Key Vault, etc. It's a way to pivot and escalate within Azure.
Got it. Moving over to Google Cloud Platform, GCP hacking highlights. Similar patterns here, enumerating cloud storage buckets.
Yep, very similar. GCP has cloud storage buckets. You can use the gatesutl command line tool to interact with them. Commands like gatesutl LLs list buckets or objects. gsutl IAM get gs.bucket name retrieves the IAM policy for a bucket, showing permissions. And tools like GCP Bucket Brute specifically hunt for publicly accessible buckets by trying common naming patterns.
And enumerating Google Cloud service accounts.
Service accounts are identities for applications or VMs in GCP. Attackers try to list service accounts within a project. If they compromise a user or resource with the permission to impersonate a service account, they can generate access tokens for that service account and then use its privileges. Again, it's about finding and leveraging identities.
Okay, platform specifics are key. What about the container world? Container Kubernetes hacking highlights. Exploiting the Docker Remote API.
If an attacker gets administrative access to the Docker host machine, they can often interact with the Docker daemon via its API, often exposed via a Unix socket or network port. This gives them immense power. They can use Docker commands, Docker inspect, Docker exec, to peek inside running containers, potentially stealing environment variables containing secrets, Docker exec container n. They can copy files from the host into a container, or from a container to the host, Docker chippy. They can start new containers, maybe with privileged access or mounting sensitive host directories. They could even use a container to scan the internal network, Docker run map. If a database like MySQL is running in a container, Docker's on Docker Merskill, they might try to extract its credentials using Docker exec.
So compromising the Docker host is pretty critical. What about Kubernetes privilege escalation directly within the cluster?
Several routes there too. Compromising a master node is huge, especially getting access to the API server, kubeapp server, or the etc. data store. As we said, etc. holds all the cluster secrets and configurations. An attacker with etc. access essentially owns the cluster. They can read secrets, modify deployments, create admin users. Commands like keysf grep app-server might reveal the etc. location, and etc. get registry secrets tries to dump secrets. Compromising an individual worker node, via the kubelet agent for example, can also allow escalation, maybe by deploying privileged pods onto that node. Even compromising a single container can lead to escalation if it's misconfigured, for instance, if it mounts a sensitive host directory using a host path volume. An attacker in the container could then potentially read or write files on the underlying node.
Wow. It really seems like across all these platforms, the common threads are misconfigurations, weak access control, and exposed secrets. That's where ethical hackers often find their way in.
That's absolutely right. While zero-day exploits exist, the vast majority of successful cloud breaches leverage these fundamental weaknesses. The complexity and dynamic nature of the cloud make it really hard to get everything configured perfectly and keep it that way. That's the battleground.
It's a huge challenge. Now that we've seen how attackers operate, how do organizations actually defend against these constantly evolving threats? What does good cloud security look like?
That's the crucial next step. And the foundation for all cloud security starts with understanding that shared responsibility model we touched on earlier.
Cloud security protecting the digital sky.
Right. That model is so important. Just a recap, it's about security being a joint effort between the cloud provider and the customer. And the responsibilities change depending on the service model, IaaS, PaaS, SaaS.
Exactly. Let's quickly nail that down again because it's fundamental. II provider secures the cloud. Physical stuff, network, hypervisor. Customer secures in the cloud, OS, apps, data, network config, IAM. They build the house. You secure everything inside. Paid's provider secures more, infrastructure, OS, middleware, runtime. Customer secures their applications and data running on the platform. They provide the secure house structure. You secure your furniture and belongings. SaaS provider secures pretty much everything. Infrastructure, platform, application. Customer responsibility is mainly limited to data access, user management, and configuration within the app. They manage the furnished apartment. You control who gets a key to your unit and what they do inside. Understanding this isn't just paperwork, it's the absolute first step. If you don't know what you're responsible for, you can't secure it. It tells you where to focus your security efforts and resources.
Crystal clear. Beyond knowing who does what, good security usually involves multiple layers, right? What are the key cloud security control layers?
Yeah, you need defense in depth. Thinking in layers helps. Application layer. This is about securing the code itself, using secure coding practices like OSP standards throughout the development lifecycle, SDLC. Using web application firewalls, WFs, to filter bad traffic before it hits the app. Doing static and dynamic analysis of the code, trusted computing. This focuses on creating a secure and verifiable environment, using things like hardware root of trust, ROOT-TA, to ensure the system boots securely and hasn't been tampered with, ensuring auditability. Computation and storage. This involves policies for how data is handled, storage, retention, backup. Implementing security controls at the compute storage level, like host-based firewalls, intrusion detection prevention systems, IDSC, file integrity monitoring, and critically, data encryption at rest and in transit, and data masking. Physical layer. This is the provider's main domain, but still important. Security of the actual data centers, guards, gates, guns, CCTV, biometric access, environmental controls.
Okay, defense in depth. Now let's give our listeners some practical advice. What are some key cloud security concepts and general best practices they should be implementing?
Absolutely. Let's get actionable. First, embrace zero trust networks. The old castle and moat idea doesn't work well in the cloud. Zero trust means never trust, always verify. Assume threats can come from anywhere, inside or outside. Requires strict identity verification, least privilege access, microsegmentation, isolating workloads, and continuous monitoring of everything. Implement a Cloud Access Security Broker, CASB. A CSB acts like a control point, a security policy enforcement engine between your users and your cloud services. It gives you visibility into cloud usage, finding that risky shadow IT, enforces data security policies like encryption or preventing sensitive data uploads, protects against threats like compromised accounts or malware, and helps ensure compliance. Can be on-prem or cloud-hosted. Deploy data loss prevention DLP solutions. These tools scan data in use, in motion, and at rest to detect and block potential exfiltration of sensitive information. Often works closely with a CASB. Enforce multi-factor authentication, MFA everywhere. Seriously, everywhere. For user accounts, admin accounts, service accounts where possible. It's one of the single most effective controls against credential theft. Establish robust logging and monitoring. You need visibility. Collect logs from everything, cloud provider APIs, operating systems, applications, network devices, centralize them, protect them, and actively monitor them for suspicious activity. You can't respond to what you can't see.
That's a solid list. Zero trust, CASB, DLP, MFA, logging. Seems crucial. But with all this complexity, especially in multi-cloud setups, How do organizations make sure they're making good choices with providers and keeping their own house in order?
But that's where diligence comes in. Using checklists and structured assessments is really important. Before signing up with a provider, assess their security posture, their compliance certifications, their incident response processes. And internally, assess your own readiness. Is your security team trained for the cloud? Do you have clear policies? How will you handle incidents? What technical controls are in place? Data separation, auth-key management? It's about asking the hard questions before you migrate critical workloads.
Makes sense. Do your homework. Are there also specific best practices for the major platforms we discussed, like platform-specific security best practices?
Definitely. While the general principles apply, each platform has its own nuances and specific tools. For AWS, use IAM Access Analyzer to find overly permissive policies. Implement strong network segmentation with security groups and network ACLs. Use AWS WEF for web protection. Leverage Amazon Inspector for vulnerability scanning of EC2 and containers. Use GuardDuty for threat detection. For Azure, enforce MFA rigorously via Azure AD conditional access. Use network security groups, NSGs, for segmentation. Use just-in-time JIT VM access to limit standing privileged access. Implement strong operational security through Azure Security Center recommendations. Use Azure Sentinel for SUMSAR for Kubernetes. Implement fine-grained role-based access control, RBAC. Use network policies to restrict pod-to-pod communication. Scan container images for vulnerabilities before deployment. Use pod security policies, or the newer pod security admission, to enforce security contexts, like preventing privileged containers. For serverless, apply the principle of least privilege religiously to function execution rules. Perform strict input validation on all event data. Follow secure coding practices within the function code itself. Use tools to scan dependencies. For Docker, always use trusted base images and scan them. Keep the host OS and Docker daemon patched. Secure the Docker API endpoint, use HTTPS authentication. Use Docker volumes for sensitive data. Don't store it in the container image or file system directly.
Okay, great platform-specific tips. And finally, there are tools to help manage all this, right? Tools for cloud security posture management, CSPM.
Yes, CSPM tools are essential for managing security at scale in the cloud. Tools like Scout Suite are open-source multi-cloud auditing tools. They check configurations against best practices. Commercial platforms like Qualys Cloud Platform offer continuous assessment, vulnerability management, and compliance monitoring across hybrid environments. And specialized tools like Advanced Cluster Security for Kubernetes from Red Hat ABM, or similar products from vendors like Aqua Security or Palo Alto Networks focus specifically on securing Kubernetes environments: visibility, compliance, threat detection, runtime defense.
So these tools automate the checking and give you that crucial visibility across complex dynamic cloud setups.
Exactly. Trying to manually track thousands of resources and configurations across multiple clouds is impossible. CSPM tools provide that necessary automation and continuous monitoring to help organizations stay on top of their security posture. Recap.
Okay, wow. So what does this all mean? We have covered a ton of ground today, diving deep into cloud computing for ethical hackers, guided by the CEHv13 Module 19.
We certainly have. It's a big topic.
Let's try and boil down some key takeaways. First, cloud computing isn't monolithic. It's diverse IaaS SaaS models, complex deployments, public, private, hybrid, multi, distributed, polyclouds. Each choice profoundly impacts control and security responsibility. Second, new tech like VR leverages cloud scale, while fog and edge computing are reshaping how we handle IoT data by processing it closer to the source. Third, containers, Docker and orchestration, Kubernetes, are fundamental for modern scalable apps, but they bring unique security challenges around image security, secrets, isolation, and communication. Fourth, serverless offers amazing agility but shifts security focus to function permissions, inputs, and dependencies, with ephemeral execution making detection harder. Fifth, ethical hacking in the cloud requires platform-specific knowledge. We saw techniques for recon and exploitation across AWS, Azure, GCP, and Kubernetes, often targeting misconfigs and weak access controls. And finally, maybe most importantly, cloud security is a shared responsibility. It absolutely demands robust controls, best practices, and continuous vigilance from both the provider and the customer.
Well summarized. And that last point is key. The cloud's dynamic nature means security isn't a set-it-and-forget-it task. It's an ongoing journey of adaptation and vigilance. For ethical hackers, it means constant learning. For organizations, it means proactive, continuous security management. Outro.
And that brings us to the end of this deep dive. Thank you so much for joining us on this pretty extensive exploration of cloud computing from an ethical hacking perspective. It's a field that's just moving incredibly fast, and honestly, staying informed is probably your best defense. So here's a final thought to chew on. As cloud environments get even more complex, maybe blending edge, fog, and multiple public clouds, how might that shared responsibility model blur even further? And what new kinds of zero-trust thinking will we need to really secure our digital future, especially with things like AI-driven attacks emerging? Something to think about. Keep exploring this vital field on your own. Until next time, stay curious, stay secure, and keep diving deep.